I'm going to tell you something that sounds like complete nonsense. Ready? The universe could be finite, meaning it contains a limited, countable amount of space and yet have no edge. No boundary, no place where you can go and say, here, this is where it ends. You think that's a contradiction. Finite means limited. Limited means bounded. Bounded means there's an edge somewhere, right? Wrong. Completely, utterly, beautifully wrong. Think about the surface of the Earth. It's finite. There's only so much area on it. Roughly 510 million square kilometers. You can measure it. You can count it. It's limited. But where's the edge? Where's the boundary? If you start walking in one direction and keep going, do you eventually fall off? No. You walk around the whole planet and come back to where you started. The surface is finite but has no edge. It's endless, even though it's not infinite. Now take that idea, that shocking, mind-bending geometric fact, and apply it to the entire three-dimensional universe. Not just the surface of a sphere, but the volume of space itself. That's what cosmologists are seriously proposing. And the evidence? It's right there in the data, if you know how to look. Finite but endless, limited but unbounded. That's not poetry. That's geometry. And it's going to break your brain in the best possible way. What does it mean for space itself to be curved? Let's start with the thing that confused me for years when I was first learning about this stuff. And I mean, genuinely confused. I asked multiple people, read multiple textbooks, and kept getting answers that didn't quite click. The confusion is this: what does it even mean for space itself to be curved? You've probably heard that Einstein's general relativity says massive objects curve space-time. The sun curves space around it, and that's why the Earth orbits its following a straight line through curved space. Fine, I get that. The presence of mass energy curves the geometry. Makes sense. But when cosmologists talk about the large-scale geometry of the universe, whether it's flat, positively curved, or negatively curved, they're not talking about local curvature caused by stars and galaxies. They're talking about the intrinsic curvature of space itself on the largest scales, independent of any particular mass distribution. And that's where people get lost. Because we're used to thinking about curvature as something embedded in a higher dimensional space. A sphere is curved because it's a two-dimensional surface embedded in three-dimensional space. You can see the curvature from the outside. But when we talk about the universe being curved, there's no outside. The universe is everything, all of space. So what does it mean for space itself to be curved if there's nothing outside of space to curve INTO? This is where you have to let go of your intuition and trust the math. And the math says curvature is intrinsic. You don't need an embedding space to define it. You can measure curvature entirely from the inside just by doing geometry. Here's how. Imagine you're a two-dimensional creature living on a surface you can't see up or down. You only know left, right, and forward, backward. You want to know if your surface is curved. How would you check? Easy. Draw a triangle, measure the angles, add them up. In flat space Euclidean geometry, the angles of a triangle always add up to 180 degrees. Exactly. No exceptions. But on a curved surface, that's not true. On the surface of a sphere-positive curvature, the angles add up to more than 180 degrees. Draw a big triangle on the Earth, say from the North Pole to 2 points on the equator. Each of those equator to pole lines is perpendicular to the equator, so those two angles are 90 degrees each. That's already 180 degrees, and we haven't even counted the angle at the North Pole yet. Total, more than 180. On a negatively curved surface, a saddle shape, a hyperbolic geometry, the angles add up to less than 180 degrees. You don't need to see the surface from the outside to make this measurement. You just do geometry on the surface itself, and the angles tell you whether you're on a sphere, a plane, or a saddle. That's intrinsic curvature. And it works the same way in 3 dimensions. You don't need to imagine the 3-dimensional universe embedded in some hypothetical 4-dimensional space. You just measure triangles. Or more precisely, you measure how light rays travel, how distances add up, how volumes scale. The geometry itself tells you if space is curved. Now here's where it gets cosmologically interesting. General relativity gives us a set of equations, the Einstein field equations, that relate the curvature of space-time to the distribution of matter and energy. When cosmologists apply those equations to the universe as a whole, assuming the universe is roughly homogeneous and isotropic on large scales, which observations support, they get 3 possible geometries. 1, the universe is flat. Euclidean geometry works. Parallel lines stay parallel. Triangles add up to 180 degrees. Space goes on forever in all directions, infinite and unbounded. 2, the universe has positive curvature. It's like the surface of a sphere, but in 3 dimensions. This is called a closed universe. It's finite in volume, but has no boundary. If you travel in one direction long enough, you come back to where you started, like walking around the Earth, but in 3D. 3, the universe has negative curvature, hyperbolic geometry, saddle-shaped, but again in 3 dimensions. This is called an open universe, and it's infinite. It goes on forever, just like the flat case. But the geometry is different. Which one do we live in? That's an observational question. And the answer depends on a single number, the density parameter, usually written as omega. Omega is the ratio of the actual density of the universe to the critical density, the density at which the universe would be exactly flat. If omega equals 1, the universe is flat. If omega is greater than 1, the universe is closed, positively curved. If omega is less than 1, the universe is open, negatively curved. Measuring omega is one of the great challenges of observational cosmology. You have to add up all the matter, all the energy, all the dark matter, all the dark energy, and compare that to what general relativity says is needed for flatness. And here's what we found, as far as we can tell. To within the precision of our measurements, omega is 1. The universe appears to be flat, or very, very close to flat. But, and this is important, our measurements aren't perfect. There's some uncertainty. It's possible that the universe is very slightly positively curved, omega is slightly greater than 1, and we just can't measure the difference yet because the curvature radius is so enormous. If the universe is closed, it's a very big sphere. And that brings us to the shocking possibility. The universe might be finite in volume, but so large that it looks flat to us, the same way the Earth looks flat when you're standing in a field. The curvature is there, but it's too gentle for us to detect over the distances we can measure. If that's true, if the universe is closed, then it's finite but has no edge. You could, in principle, point your spaceship in one direction, fly in a straight line for an incomprehensibly long time, and eventually arrive back at Earth from the opposite direction. Finite, but endless, limited in volume, unbounded in extent, no edge, no boundary, no place where space just stops. And the geometry that makes this possible is not some abstract mathematical fantasy. It's the same geometry that describes the surface of the Earth, just 1 dimension higher. That's not magic, that's just curvature. The universe doesn't need an outside, okay? So we've established that a finite, edgeless universe is geometrically possible. It's not a contradiction. It's just a closed 3-dimensional manifold with positive curvature, a 3-sphere, if you want to be technical about it. But now I want to address the thing that probably bothers you the most. The thing that bothered me the most when I first heard this. If the universe is finite, if it curves back on itself, doesn't that mean it has to be embedded in some higher dimensional space? Doesn't the 3-sphere have to sit inside a 4-dimensional Euclidean space the same way a 2-sphere sits inside 3-dimensional space? The answer is no. Absolutely not. And understanding why is one of the most important conceptual leaps you can make in geometry. A sphere, a 2-sphere, the surface of a ball, can be embedded in 3-dimensional space. That's how we usually visualize it. But the sphere doesn't need that embedding to exist. The sphere is a perfectly well-defined geometric object all by itself, intrinsically, without reference to any external space. You can describe the geometry of a sphere entirely in terms of distances measured on the sphere. You never have to mention the 3rd dimension. You can write down the metric, the formula that tells you how to calculate distances between points, and that metric completely characterizes the geometry. For a 2-sphere of radius r, the metric in spherical coordinates is ds squared equals r squared theta squared plus sin squared theta d phi squared. That's it. That formula tells you everything about the geometry of the sphere. You can calculate distances, areas, angles, curvature, all without ever talking about a 3rd dimension. The embedding is a visualization tool. It's useful for humans because we're 3-dimensional creatures and we can picture a sphere embedded in our familiar 3D space. But mathematically, the embedding is not necessary. The sphere exists as an abstract geometric space, and all its properties can be derived from the intrinsic metric. The same is true for the 3 sphere, the three-dimensional analog of the two sphere. We can't visualize it because we can't picture four-dimensional space, but we can describe it. We can write down its metric. We can calculate how distances work, how volumes scale, how geodesics behave. The three-sphere is a perfectly well-defined geometric object, and it doesn't require an embedding in four-dimensional Euclidean space to exist. Now, you might say, but surely there's some sense in which the universe is embedded in something. It has to exist in some larger context, right? And the answer is no, not in any physical sense. The universe is not embedded in anything. The universe is all there is. There is no outside. The geometry of the universe is intrinsic, and it's described entirely by the metric, the rule that tells you how to measure distances and angles within space-time itself. When general relativity talks about curved space-time, it's talking about the intrinsic curvature of a four-dimensional manifold, 3 dimensions of space plus 1 of time. That manifold is not sitting inside some 5-dimensional space. It's just space-time. That's it. That's all there is. This is hard to wrap your head around, I know, because every curved thing you've ever seen in your life, a ball, a bowl, a saddle, is embedded in the 3-dimensional space you live in. Your intuition is screaming at you that curvature requires an embedding. But your intuition is wrong. And the only way to get past this is to really, truly internalize what intrinsic geometry means. The curvature is a property of the space itself, measurable from within without reference to any external space. Let me give you an analogy that might help. Imagine you're playing a video game, a two-dimensional game, like an old-school platform. The game world is a 2D surface. Maybe it's flat, maybe it wraps around like the old Asteroids game. Now ask yourself, is that 2D game world embedded in some higher dimensional space? Well, from the outside, from your perspective, as a player in the real world, the game is being rendered on a screen, which is a physical object in 3-dimensional space. But from the perspective of a character inside the game, there is no higher dimension. The game world is all there is. The character can measure distances, navigate obstacles, interact with objects all within the 2D space of the game. The game world has its own intrinsic geometry, and that geometry doesn't depend on the fact that you're viewing it on a screen. The universe is like that. We're characters in the game. The universe has its own intrinsic geometry, and we measure that geometry from within. There's no player sitting outside looking at us on a screen, and there doesn't need to be. The game is the reality, okay? Now let's talk about what it would actually be like to live in a finite, closed universe. First of all, if the universe is closed and finite, there's a maximum distance you can be from any point. If you're on a 2-sphere, the farthest you can be from any point is half the circumference, the distance to the antipodal point. On Earth, that's about 20,000 kilometers. Go any farther and you start getting closer again, coming around the other side. In a closed 3 universe, the same thing applies. There's a maximum distance. If the universe has a radius, r, where radius is a measure of the curvature scale, not a distance to a center, remember, there's no center, e, then the farthest you can be from any point is roughly pi r, the 3-dimensional analog of half the circumference of a circle. Now, how big is r? We don't know. If the universe is closed, our measurements suggest r is at least as large as the observable universe, at least 46 billion light years, probably much larger. It could be hundreds of billions of light years. It could be trillions. We just don't know. But if it's finite, then there's a finite amount of space, a finite volume, and a finite amount of stuff in the universe, not infinite. Countable, limited, and that means, this is wild, if you could travel far enough, you could come back to where you started. You could circumnavigate the universe. Of course, far enough might be so absurdly far that it's physically impossible. If the universe is expanding, which it is, and the expansion is accelerating, which it is, then even traveling at the speed of light, you might never complete the loop before the expansion carries you too far away. But in principle, if the universe is closed, the loop exists. And here's an even weirder consequence. If the universe is closed and finite, then when you look out into space with a telescope, you might be seeing the same galaxy multiple times, once in its current location, and again as light that is looped all the way around the universe. Imagine pointing your telescope in one direction and seeing a galaxy 10 billion light years away. Now point your telescope in the opposite direction. You see another galaxy, also 10 billion light years away. But what if those are the same galaxy? What if the light from that galaxy has traveled all the way around the universe and reached you from the opposite side? This is called a cosmic hall of mirrors effect. In a sufficiently small, closed universe, you'd see multiple images of the same objects, repeated in different directions, at different distances, at different ages. We haven't observed this. If it's happening, the universe is too big for us to detect the repeats. But it's a testable prediction. If the universe is closed and small enough, we should be able to find matching patterns in the cosmic microwave background or in the distribution of galaxies, the same structures appearing in different parts of the sky. People have looked. So far, nothing. Which means if the universe is closed, it's big, really big. Bigger than the observable universe by a significant factor. But the possibility is there, finite, endless, repeating, a closed loop of space that contains all of existence and yet has no boundary. That's not science fiction. That's a serious, respectable, cosmological model. And the only thing standing between us and confirming it is better measurements of the geometry of the universe. Topology is weirder than geometry. Now let me tell you about a different way. The universe could be finite but endless, because the three-sphere, the closed, positively curved universe, is not the only game in town. There's a whole zoo of possible topologies, and some of them are much weirder than a simple sphere. Topology is the study of shapes and spaces, but it's not about distances or angles. It's about connectivity, about which points are connected to which other points, and how the space is stitched together. Two spaces can have the same geometry, the same curvature, the same metric, but different topologies. And that difference matters, because topology determines the global structure of the universe. Let me give you the simplest example, the flat torus. Start with a flat two-dimensional plane, infinite in extent. Standard Euclidean geometry. Now take a rectangular piece of that plane and do something clever. Identify the opposite edges. Glue the left edge to the right edge and the top edge to the bottom edge. What you get is a torus, a donut shape. But here's the thing, the geometry is still flat. The intrinsic curvature is 0. If you're an ant living on the surface, doing measurements locally, you'd find that triangles add up to 180 degrees, parallel lines stay parallel, all the rules of Euclidean geometry apply. But globally, the space is finite. There's only so much area. If you travel in one direction, you wrap around and come back to where you started. The space is finite, but it has no edge. You never hit a boundary, you just loop around. This is a flat torus. Same local geometry as an infinite plane, but completely different global topology. Now take that idea and extend it to 3 dimensions. Start with flat, infinite 3D space. Take a box, a 3-dimensional rectangular region. Identify opposite faces. Glue the left face to the right face, the front face to the back face, the top face to the bottom face. What you get is a 3 torus. It's flat, 0 curvature everywhere, but it's finite in volume, and it has no boundary. If you travel in any direction, you wrap around and come back. This is another way the universe could be finite, but endless. Not curved like a sphere, flat, but with a non-trivial topology that makes it finite. And it doesn't have to be a torus. There are other possibilities. You can do more complicated identifications. You can twist the edges before you glue them. You can create spaces with all kinds of bizarre global structures. The Poincaré dodecahedral space, the Hanchi-Wendt manifold, the Klein bottle in 3D, not just 2D. The list goes on. These are not just mathematical curiosities. These are serious candidates for the actual topology of the universe. And the reason they're serious is that they're consistent with observations. Remember, locally, on scales, we can measure directly, the universe looks flat. Curvature, if it exists, is very small. So if the universe has a non-trivial topology, if it's a 3 torus or something even weirder, we might not be able to tell just by measuring curvature. We'd have to look for global signatures. What kind of signatures? The cosmic hall of mirrors effect I mentioned earlier. Repeating patterns in the cosmic microwave background. Matching structures in opposite parts of the sky. Specific correlations that shouldn't exist in an infinite universe but would exist in a finite one with a periodic topology. People have searched for these signatures. Some claim to have found hints, weak signals, tantalizing patterns, but nothing definitive. The data is noisy, the analysis is complicated, And the universe is big enough that even if it has a non-trivial topology, the repeat scale might be larger than the observable universe, in which case we'd never see the pattern. But the possibility is there. The universe might be a 3 torus. It might be flat, finite, and endless all at once. And we might never know for sure, because the topology might be too large for us to measure. That's both frustrating and exhilarating. Frustrating because it means there are fundamental questions about the universe. Is it finite? What's its topology? That might be empirically undecidable with the data we can access. Exhilarating because it means the universe might be far stranger, far more intricate than we give it credit for. Now let me hit you with something even more mind-bending. All of this, the 3 sphere, the 3 torus, all these exotic topologies assumes the universe is homogeneous on large scales, that every region of space, on average, looks like every other region. Same density, same structure, same properties. But what if that's not true? What if the universe is fundamentally inhomogeneous? What if some regions are denser than others? Some regions are expanding faster. Some regions have different geometries. Then all bets are off. The simple models, flat, open, closed, don't apply. You need a much more complicated description. And the global topology could be much, much weirder. There are models speculative, not widely accepted, but mathematically consistent, in which the universe is a patchwork of different geometries stitched together. Regions of positive curvature connected to regions of negative curvature. Bubbles of different expansion rates, a cosmic quilt. In such a universe, the concept of a single global geometry doesn't even make sense. The universe doesn't have one curvature or one topology. It has many, distributed across space, varying from place to place. And in that kind of universe, finite but endless takes on a whole new meaning. Maybe the universe is finite in some regions and infinite in others. Maybe it loops back on itself in some directions, but not others. Maybe the very question, is the universe finite, doesn't have a single well-defined answer. We don't know if the universe is like that. Observations suggest it's pretty homogeneous on large scales, so the simple models are probably good approximations. But we can't rule out the possibility of something weirder. And that's what I love about cosmology. We're asking the biggest questions you can ask. What is the shape of everything? Does space go on forever? Is there an edge? And the answers are not just philosophical speculation. They're grounded in geometry, in general relativity, in observational data. We might not have the final answers yet, but we're asking the right questions. And the possible answers are more beautiful, more surprising, more conceptually rich than anything our ancestors could have imagined. Finite but endless. It's not a paradox, it's geometry. Why the shape of the universe actually matters. Let me shift gears now and talk about why any of this matters. Because you might be thinking, okay, fine, the universe could be finite or infinite, closed or open, curved or flat, with weird topology or simple topology, but does it make any difference? Does it affect anything we observe? Does it change how physics works? And the answer is yes. Surprisingly, profoundly yes. The global geometry and topology of the universe are not just abstract mathematical features. They have real observable consequences. And in some cases, those consequences are bizarre. Let's start with the simplest case, a closed, finite universe. If the universe is closed, if it's a 3 sphere with a finite volume, then there's a maximum amount of stuff that can fit inside it, a finite number of atoms, a finite number of possible states, a finite amount of information. And that has implications for thermodynamics, for statistical mechanics, for the ultimate fate of the universe. In an infinite universe, there are infinitely many regions, infinitely many galaxies, infinitely many stars. Somewhere out there, infinitely far away, there's another version of Earth, another version of you, making slightly different choices. In fact, in an infinite universe with finite entropy density, there are infinitely many exact copies of you living identical lives, because there are only finitely many possible configurations of atoms in a given volume, and if you have infinitely many volumes, you'll inevitably repeat. That's the infinite universe. Weird, but in a sort of combinatorial way. In a finite universe, that doesn't happen. There's only one of you, or at least only finitely many. The universe contains a finite amount of information, and it never repeats exactly. Does that matter? Maybe. It depends on your philosophical stance about identity, probability, fine-tuning. But it's a real difference. Now let's talk about something more concrete, the cosmic microwave background. The CMB is the afterglow of the Big Bang, a faint, nearly uniform background of microwave radiation that fills the entire universe. We've mapped it in exquisite detail using satellites like COBE, WMAP, and Planck. And what we see is remarkable. The CMB is almost perfectly uniform with tiny fluctuations, 1 part in 100,000, that represent the seeds of all the structure in the universe today. Those fluctuations are not random. They have a pattern, a specific distribution of sizes, a specific statistical signature. And the details of that pattern depend on the geometry and topology of the universe. In a flat, infinite universe, the fluctuations can have any wavelength, from tiny to arbitrarily large. But in a finite universe, there's a maximum wavelength the size of the universe itself. You can't fit a fluctuation bigger than the universe. So if the universe is finite, the CMB should show a cutoff. The largest scale fluctuations should be suppressed or absent because there's literally not enough room for them. And here's the thing, we see a hint of that. The largest scale fluctuations in the CMB are weaker than expected based on the simplest infinite universe models. It's a subtle effect, and it could be a statistical fluke, but some cosmologists think it's evidence that the universe is finite. The data isn't conclusive. The effect is at the edge of detectability. But it's there, and if it's real, it's telling us something profound. The universe has a size. Similarly, if the universe has a non-trivial topology, if it's a 3 torus, for example, the CMB should show repeating patterns, not exact copies, but correlated fluctuations in different parts of the sky, corresponding to the same structures seen from different angles as light wraps around the universe. People have searched for these patterns. Some have claimed to find them. Others dispute the analysis. It's a contentious area of research, but the principle is sound. Topology leaves fingerprints in the data. Now, here's where things get really interesting. The geometry of the universe doesn't just affect cosmology. It affects quantum mechanics. In quantum field theory, the framework that describes how particles and fields behave the structure of space-time plays a crucial role. The allowed states of a quantum field depend on the boundary conditions, the topology, the global geometry. In an infinite universe, a quantum field can have infinitely many modes, infinitely many different wavelengths, infinitely many possible states. But in a finite universe, the number of modes is finite. There are only so many ways a wave can fit inside a finite box. And that changes the physics. The vacuum energy, the energy of empty space, depends on the sum over all possible modes. In an infinite universe, that sum is infinite, leading to all kinds of nightmares. The cosmological constant problem, which I won't get into now. In a finite universe, the sum is finite, and the problem might be more tractable. This is speculative. We don't have a complete theory of quantum gravity, so we can't calculate the vacuum energy reliably in any case. But the point is, the global structure of the universe matters for quantum physics, not just classical cosmology. Here's another consequence, causality. In general relativity, the causal structure of space-time, which events can influence which other events, is determined by the metric and the topology. In a simply connected, infinite universe, causal structure is straightforward. Light cones spread outward, events influence their future. Light cones, end of story. But in a universe with non-trivial topology, things get weird. If the universe loops back on itself, then your future light cone might intersect your past light cone. You could, in principle, send a signal that travels all the way around the universe and arrives back at you in your own past. That sounds like a time machine. And in a sense, it is. Or at least, it's a closed time-like curve, a path through space-time that loops back on itself in time. Do such paths actually exist in our universe? Almost certainly not. The universe would have to be very small and very specifically structured for this to work. And even if the geometry allowed it, quantum mechanics might prevent it. There are arguments that closed time-like curves are unstable, that quantum fluctuations would blow up and destroy the geometry before you could use it to send information backward in time. But the point is, topology matters. The global structure of the universe is not just a curiosity. It has real physical consequences, and we're only beginning to understand those consequences. Cosmology is a young science. We've only had good data about the large-scale structure of the universe for a few decades. We're still figuring out the basics, the expansion rate, the matter content, the geometry. The exotic possibilities, weird topologies, finite but endless universes, cosmic hall of mirrors are at the frontier of research. But they're not fantasy. They're real possibilities, grounded in solid mathematics and consistent with what we know about general relativity and quantum mechanics. And as our observations improve, as we map the universe in more detail, we might actually be able to answer these questions. Is the universe finite? Does it have an edge? Does it loop back on itself? We don't know yet. But we're closer to knowing than ever before. And the answer, whatever it is going to be remarkable. The flatness problem and why we don't know the answer. I want to talk now about something that keeps me up at night. Not because it's wrong, but because it's right, and I don't understand why. The flatness problem, here's the thing. The universe appears to be flat, or at least very, very close to flat. The density parameter, omega, the ratio of the actual density to the critical density needed for flatness is approximately 1 to within 1% or so based on our best measurements. That sounds fine. Maybe the universe is just flat. Why is that a problem? Because flatness is UN stable. Let me explain what I mean. In general relativity, if the universe starts out slightly not flat, if omega is slightly greater or less than 1, the deviation grows over time. A universe with omega slightly greater than 1 becomes more and more positively curved as it evolves, eventually recollapsing in a big crunch. A universe with omega slightly less than 1 becomes more and more negatively curved, expanding faster and faster, diluting to nothing. Flatness omega exactly equal to 1 is a knife edge, an unstable equilibrium. If you're even a tiny bit off, you diverge rapidly. Now, wind the clock back to the Big Bang. If the universe is close to flat today, 13.8 billion years after the Big Bang, it must have been incredibly close to flat at the beginning, like absurdly close, fine-tuned to dozens of decimal places. Why? Because any deviation from flatness grows with time. If the universe was even slightly non-flat at the Big Bang, it would be wildly non-flat today. The fact that it's still close to flat means the initial conditions were tuned to ridiculous precision. This is the flatness problem. It's not that flatness is impossible, it's that flatness requires an explanation. Why was the universe born so close to flat? What set the initial conditions with such precision? The standard answer, the answer most cosmologists accept, is inflation. Inflation is a period of extraordinarily rapid expansion that supposedly occurred in the first fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10, 2, 6, and possibly much more in an incredibly short time. And here's the key. Inflation drives the universe toward flatness. No matter how curved the universe was before inflation, the rapid expansion stretches it out, smooths it out, flattens it. Like blowing up a balloon, the surface of a small balloon is noticeably curved, but if you blow it up to enormous size, any small patch looks flat. Inflation solves the flatness problem by making flatness a natural outcome, not a fine-tuned accident. The universe is flat today because inflation made it flat, regardless of what the initial conditions were. That's a beautiful idea. And there's evidence for inflation patterns in the cosmic microwave background that match the predictions of inflationary models. So most cosmologists think inflation probably happened. But, and this is what bothers me, we don't know what caused inflation. We don't have a fundamental theory of the inflaton field, the hypothetical field that drove inflation. We don't know what the initial conditions of inflation were. We don't know if inflation is eternal, or if it happened once, or if it's happening in other parts of the multiverse right now. Inflation answers one mystery by introducing another. It's progress, real progress, but it's not the final answer. And here's the thing that keeps me up. What if the universe isn't flat? What if omega is slightly greater than 1, and we just haven't measured it precisely enough to tell? If the universe is closed, if it has positive curvature and finite volume, then the flatness problem goes away, because a closed universe doesn't need to be fine-tuned to be close to flat today. It can start out with some reasonable curvature at the Big Bang, evolve according to general relativity, and end up looking nearly flat at the present time just because we happen to be living at a particular epoch in the universe's history. Think about it this way. If you're on the surface of a balloon and the balloon is small, you can tell it's curved. But if the balloon is huge, if the radius is enormous, any small patch looks flat. You'd have to measure over vast distances to detect the curvature. The same applies to a closed 3 universe. If the curvature radius is much larger than the observable universe, the universe looks flat to us, even though it's actually closed. We're like ants on a giant balloon, mistaking our local patch for an infinite plane. And if that's the case, if the universe is closed and finite, then the flatness problem isn't really a problem. It's just a consequence of living in a finite universe at a particular stage of its evolution. Of course, you still have to explain why the curvature radius is so large compared to, say, the Planck length, which is the natural scale of quantum gravity. But that's a different kind of fine-tuning problem, and it might have a different answer. The point is, we don't know. The data is consistent with flatness, but it's also consistent with slight positive curvature if the curvature radius is large enough. And depending on which of those is true, the implications for the ultimate fate of the universe are completely different. In a flat or open universe, expansion continues forever. The universe gets bigger and bigger, colder and colder, emptier and emptier, until everything decays and evaporates, and we're left with nothing but a thin gruel of radiation and black holes, and eventually even the black holes evaporate. Heat death, boring but eternal. In a closed universe, expansion eventually stops. The universe reaches a maximum size, then starts contracting. Galaxies start falling back together. The cosmic microwave background gets hotter and hotter as space shrinks. Eventually, everything crashes back together in a big crunch, the opposite of the Big Bang, a final singularity where space and time come to an end. Which one is it? We don't know. And we might not know for a long time because the measurements are so difficult. But the answer matters, not just academically, existentially. The shape of the universe determines its fate. Finite but endless might not just be a description of space. It might be a description of time, too. If the universe is closed, time might loop back on itself in some cosmological models, not in the sense of time travel, but in the sense of a cyclic universe that expands and contracts and expands again over and over, eternally. That's speculative, highly speculative, but it's not ruled out. And the fact that we can even talk about it seriously, the fact that we have the mathematics, the observations, the theoretical framework to address questions like, does time have a beginning and an end, is astonishing. We're asking the biggest questions humans have ever asked, and we're making progress. Slowly, painstakingly, but we're making progress. The universe might be finite, but endless. And if it is, we're living in one of the most remarkable structures imaginable, a closed, bounded, self-contained cosmos with no edge, no outside, no escape, a universe that contains everything and needs nothing beyond itself. And we're inside it, trying to figure it out from the inside, with nothing but our brains, our math, and our telescopes. That's beautiful. That's science. And it's the most exciting thing I can imagine doing. We're on the verge of knowing the shape of everything. Let me bring this all together, because we've covered a lot of ground, and I want to make sure you see the full picture. We started with a paradox. How can something be finite but have no edge? And the answer is, topology and geometry are not the same thing. A finite volume doesn't require a boundary. A closed surface can be finite and unbounded. And that's not a trick of language, it's a deep geometric truth. The surface of the Earth is the simplest example. Finite area, no edge. Walk in any direction, come back to where you started. And the universe, the three-dimensional space we live in, could work the same way. Not embedded in anything higher dimensional, not requiring an outside, just a closed 3 manifold with positive curvature. That's one possibility. The other is that the universe is flat but has a non-trivial topology, a 3 torus or something weirder. Finite volume, 0 curvature, no boundary. Wraparound space. A cosmic video game where leaving one edge brings you back at the opposite edge. Or the universe could be infinite, flat and infinite, or negatively curved and infinite. No edge because there's no limit space, just goes on forever. We don't know which of these is true. The data favors flatness, but doesn't rule out slight positive curvature or exotic topology. And depending on which is true, the implications are profound. If the universe is finite, there's a finite amount of stuff, a finite number of atoms, a finite number of possible states, a finite amount of information. And that means the universe is, in some sense, comprehensible. We could, in principle, catalog everything, we could count it, we could understand the whole thing. If the universe is infinite, none of that is possible. There's infinitely much to know. infinitely many galaxies, infinitely many stars, infinitely many Earths, and somewhere out there, infinitely far away, an infinite number of exact copies of you living parallel lives. Which is weirder? I honestly don't know. Both seem absurd when you think about them carefully, but one of them is true. Now, here's what I find most remarkable about all of this. We can actually address these questions. We're not just philosophizing. We're making measurements. We're analyzing data. We're testing theories. The cosmic microwave background gives us a snapshot of the early universe, and hidden in the statistical properties of that snapshot are clues about the geometry and topology of space. The distribution of galaxies tells us about large-scale structure. The expansion rate tells us about the density and curvature. We're close, tantalizingly close, to answering questions that ancient philosophers could only speculate about. Does the universe go on forever? Does it have a size? Does it have a shape? And the answer, whatever it is going to be one of the greatest intellectual achievements of our species. Because we're not gods, we're not omniscient, we're finite creatures living on a tiny rock in an incomprehensibly vast cosmos, and yet we figured out how to ask the right questions and gather the right evidence to actually learn about the shape of everything. That's incredible. That's what science is about, not having all the answers, but knowing how to find them. Let me end with a thought that's more philosophical than scientific, but I think it's worth saying. If the universe is finite but endless, if it's a closed three-sphere or a three-torus or some other compact manifold, then in a very real sense, the universe is complete. It's a self-contained whole. Everything that exists within this finite volume, and there's nothing outside it because there is no outside. That's a beautiful picture. A cosmos that doesn't need anything beyond itself. A universe that is its own context, its own reference frame, its own totality. And we're part of it. We're not observers looking at the universe from the outside. We're inside. We're made of the universe. We're patterns of atoms and energy that the universe has arranged into structures capable of thinking about the universe. In a finite universe, every atom matters. Every bit of information is part of the total. There's no infinite waste, no infinite duplication, just this one cosmos, finite and precious and complete. I don't know if that's true. The universe might be infinite. But if it's finite, if it's bounded and closed and self-contained, then there's something deeply satisfying about that. A kind of cosmic elegance. Everything in its place. Nothing wasted. Nothing duplicated. Just enough. And if it's endless, if you can travel in any direction without hitting a wall, explore forever without finding an edge, then the universe is both limited and limitless. Finite in size, but infinite in possibility. A paradox that's not a paradox once you understand the geometry. That's what I love about this subject. It's not just abstract math. It's the shape of reality, the structure of everything. And the fact that we can even comprehend it, that we can look at the data, do the calculation, and figure out whether we live in a finite or infinite cosmos is one of the most astonishing things about being human. We're small, we're brief. We live on a speck of dust in an ocean of space, but we can think, we can measure, we can understand. And right now, today, we're on the verge of answering one of the oldest questions in human history. What is the shape of the universe? The answer might be finite but endless, limited but unbounded, a closed loop of space with no edge, no boundary, no outside. Or the answer might be infinite, forever, unending in all directions. Either way, the answer is going to be beautiful. Because the universe, whatever its shape, is governed by laws we can understand, structured by geometry we can describe, observable through telescopes, and analyzable with mathematics. The universe is knowable. Not completely. There are edges to knowledge, horizons beyond which we cannot see. But within those horizons, within the bounds of what's accessible to us, there's so much to learn, so much to discover, so much beauty. Finite but endless. That's not just a description of the universe. It's a description of science itself. We have finite lifetimes, finite resources, finite brains. But the questions we can ask, the discoveries we can make, the understanding we can achieve, that's endless. There's always another question, always another puzzle, always another horizon to explore. And that is what makes it all worthwhile. So the next time you look up at the night sky, think about this. You might be looking at light that has traveled halfway around the universe. You might be seeing a galaxy that exists on the far side of a cosmic loop, an image carried to you by photons that have circumnavigated all of space. Or you might be looking out into an infinite void, an endless expanse that goes on forever, with no boundary, no edge, no end. We don't know yet, but we're working on it. And one day, maybe in our lifetimes, maybe not, we'll know. We'll know the shape of everything. And when we do, it's going to blow our minds.